And then each other, cancel out, so like this one, like A, add the C2 cancel out, like A is 7, C1 is 4. And you just solve for C2 is 4 to 7. And then for C1.
So there are many
this and that.
physical situations when the problem itself requires a system of equations. But in addition to these cases where naturally it demands a system of equations, there are also times when you want to transform a higher order differential equation into a system of differential equations. And part of the reason is if you're solving differential equations numerically, trying to find approximate solutions, there are many good algorithms out there developed for system of first order differential equations, the most famous of which is called the Runge-Kutta method. These methods are good for systems. So in order to use those methods to solve the higher order differential equation, they would first change this into a first order system. Okay? Now let me show you by example how that can be done. So here's an equation, y double prime minus 3y prime plus 2y equal to 0. Here's a second order differential equation. And I want to come up with a system of equations that's equivalent to this. Now, the first thing that you do is just first set y1 as y. And you write y2 as y prime. Okay, so set the function itself as y1 and set the derivative as y2. Now if you do this, then the question is, what is y double prime equal to? No, instead of using y3, you just want to use y1 and y2. Yes. So y double prime is the derivative of what? Derivative of?
Y2.
Y2. And then, because y2 is the derivative of y, and y is equal to y1, you have the following identities. First, y2 is the derivative of y1 prime. That's just from this step. Because y is same as y1, this is the first thing that you get immediately. This is always, whenever you change a second order differential equation to system of first order, this is always there. Okay? Now, where do we get to use this? Well, you get to use it here. So look, this one is y double prime is y2 prime minus 3, and then these can be written as y2 and y1, right? y2, y1 equals to 0. And then if I move these other ones to the other side, then we have the following system. Look at what we have. I know that y1 prime is y2, and I know that y2 prime, if you move these to the other side, this is negative 2y1, and this move to the other side is plus 3y2. Hence, we have a system of two functions with first order. This is a first order system of two functions. So likewise, if you have a third order differential equation, then you can define y1, y2, y3 that way, and y3 prime will be y to the third the third derivative of y, and the third derivative equation can be, third order differential equation can be transformed into a system of three functions, three differential equations with first order. Okay, you can do that. Okay. Now, one fun thing to do at this point is to actually solve this differential equation as using the eigenvalues and eigenvectors, and compare that with the solution that we get from the solution of this original one. Try this. So let's try it. So what is that in eigenvalue? What's that in the matrix form? The 0, 1, because this is 0 times y1, you put 0, 1, negative 2, 3, y1, y2. That's the differential equation in matrix form. So if I take the characteristic equation is negative lambda, 1, negative 2, 3 minus lambda. If you multiply this, negative lambda times 3 is negative 3 lambda. Negative lambda times negative lambda is positive lambda squared. Negative 2, and then you're subtracting negative 2, so it's plus 2. So that gives you lambda minus 2, lambda minus 1 equal to 0. So our eigenvalues are 2 and 1, right? So for each case, let's try to find out the eigenvectors. Lambda equals to 2 gives you negative 2, 1, something, something, I don't care. And I need a, b, and it has to be 0, 0. So if you write down the equation, that's negative 2a plus b equal to 0, which gives you, if you set a as 1, b would be 2. That's the eigenvector. And for lambda equals to 1, this will be negative 1, 1, something, something, a, b. So that gives you negative a plus b equal to 0. So 1, 1 will be the eigenvector that corresponds to the eigenvalue. And therefore, now we are ready to say y1, y2 is c1 times the first eigenvector, which is 1 and 2, times the first eigenvalue we chose, 2t, plus c2 times the eigenvector e to the eigenvalue, 1t. So that's the equation. Now, what's the solution of the original equation then? y1 is same as y, right? So the solution of this should be the y1. So what is y1? y1 is c1 times 1 times e to the 2t, and c2 times 1 times e to the t, so it's c2 e to the t, right? Now, what's the characteristic equation for this one? R squared minus 3r plus 2, right? What are the two solutions? 2 and 1. So you get 2 and 1, so that's again the solution. So you get same answer whether you change it to a system and solve, or you use the original method, which is much quicker, but it's just a demonstration that this way of solving does work.
You don't solve, or you don't put the YT thing up there?
No, I just want to verify that I get the same answer regardless of using it this way or the old way that we were taught to. Gives you the same answer. Of course, y2 will be just the derivative of this. So if you differentiate this, what do you get? 2 comes down. And e to the t differentiates the e to the t, so that's what it is. That's your y2, right?
I thought you would.
No, it's actually the same thing. y2 is 2c1 e to the 2t plus 1c2 e to the t. Same thing, isn't it? So whether you take this one and differentiate to get the next one or this one, it's the same thing. The reason that you can get y2 by differentiating the first one is because it satisfies this. Do you have any questions on this one? Is there any calculation?